Hi all, in this video I want to draw the mechanism for these two aldol condensations. The final product will be an alpha-beta unsaturated ketone, or in general, an alpha-beta unsaturated carbonyl. Let's do the first one together, and then I'll give you an opportunity to do this one on your own. When we look at this aldol condensation, we know that we're going to make an enolate. The ketone here is symmetrical, and we could use either the alpha carbon on the left or the alpha carbon on the right. And that alpha carbon should be this one right here. And we attacked the dot of the other carbonyl. So right now I'm not drawing the mechanism, but I am planning out the key bond connections. It will be between this alpha carbon and this dot over here. Okay. When you start a mechanism, you should draw the starter material. Make sure also that you show the electrons that are moving explicitly. I like to say that every mechanism arrow has to start from a source of electrons. We are making the enolate. We are going to strip off an alpha hydrogen and make the enolate. We're going to do that with a base. We have an oxide base. This is ethoxide. It is the student's responsibility to separate the ionic compound into Na plus and OET minus. So that's an ethyl. Okay. Grab the proton. I don't want to make the carbon anion. I want to make the more stable, the more contributing resonance structure, which is the O minus. The aldol reaction and the condensation following that are all reversible steps. So there's my equilibrium. I'll draw the attacker. Oh no, we don't even have an attacker yet. We have the enolate, and then the enolate attacks. Okay. The enolate, I like to use an O minus enolate form, and I'll draw it like this. Right now, it doesn't really matter since they're trans, you get a mixture. We did create ethanol. I'll draw that down here, but it's not used in the next step. In the next step, we have the enolate. Maybe I should label some of this stuff. This is the enolate. You know that there is a resonance. Maybe your professor will require you to draw the resonance structure, but I don't in a mechanism. I may ask in a different problem, show the mechanism of the resonance, but here I just want to show the mechanism of the reaction. We're going to bring in another ketone, another one of itself, but again, it's not the enolate form. We need some enolate and we need some unreacted. And now we go ahead and do the attack to make a tetrahedral intermediate. And let's see what we get. You attack the dot. You have the O minus. On that dot, you have two alpha groups, 1 and 2. We had ethanol before. We also have some water. It doesn't matter really in this reaction which one you use to protonate the oxygen. Just a word of advice. If you are under basic conditions, which we are, that's sodium ethoxide base, you should never have a protonated oxygen. Okay, that doesn't exist in base. The complement is if you're under acidic conditions, you should never have an O minus. So you want to keep that in mind. That's a really good rule of thumb when you're working with acid catalysis or base catalysis. Here we have under base, so we're never going to have like a leaving group that's water, or we're never going to be protonating the carbonyl group under basic conditions. So this is fine. We get the ethoxide back. And what do we have? I call this the aldol product. Not the aldol condensation, just the aldol product. We're going to keep going and do the condensation. We get to the aldol product in 3 steps. Now the condensation specifically is a dehydration, or you can think of it as elimination of water. All of those words mean the same thing. I don't know if I emphasized that in the previous video, but dehydration is the elimination of water, and dehydration is a type of condensation. So we have a base. We did create a base actually in the previous step. We made the ethoxide again. We're going to use it. We're going to strip off this hydrogen here, which is still an alpha hydrogen. Okay. Now, the danger is when you grab this proton, it's very tempting to make the double bond to the right and kick out OH minus. But in different experiments, it was realized that we make the enolate again. So experiments support the formation of this O minus again. And what do we have here? We have the OH. I think that's all the carbons. We have the dots. Just so I keep track, this is the alpha. Okay, we made a double bond here. So let me draw that like that. Okay, let me label this as a tetrahedral intermediate. And it's important when you strip off the second alpha proton that you make the enolate again. This enolate does have, we call this a beta hydroxy. If you want, I don't normally label, or I don't normally remember that we make the beta hydroxy, but here we do. Beta hydroxy enolate. This is the aldol product. The aldol product is typically a beta hydroxy carbonyl, either a ketone or aldehyde. Okay, this one I do typically remember because my final product is not the beta hydroxy carbonyl, it's the alpha beta unsaturated carbonyl. See how it's unsaturated? You have a double bond between alpha and beta. Okay, now we're ready for our last step. If you recall from the previous video where we first introduced the aldol condensation, it was 5 steps. 1, 2, 3, 4. The last step is actually the rate determining step, the slow step. It's a step in which the OH is finally kicked off to do the dehydration. And we get our final product. Did I draw that right? Okay, I'm checking the number of carbons. This is our final product. This is the aldol condensation product. But like I said before, it is also the alpha beta double bond, so it's not saturated, it is unsaturated ketone, or in general carbonyl. Okay. See the difference between those two. This is step 6. I probably won't require my class to label the rate determining step, but the rate determining step is the last step. It's a step in which the leaving group leaves. Oh, so we did kick out OH minus, so let me draw that here, like that. What's interesting about this ultimately dehydration is that it's a dehydration that you typically do not learn in Organic Chemistry 1. In Organic Chemistry 1 you learned E1 and E2, but this is a special type of E1. So, how do I want to write this? The dehydration step is called an E1CB. Dehydration step. Is E1 subscript CB. Both little C and a B. What's going on? C, B. That's considered unimolecular elimination conjugate base because we did get the conjugate base of the aldol product. We go through the anion. We don't go through the carbocation like we do with a acid catalyzed dehydration. Okay, and we definitely don't do an E2 because here we don't have a helper molecule. It's one molecule going through the rate determining step. This, I think, is useful to keep in the back of your mind because, again, it will prevent you from doing the dehydration here in step 4 because you want to form the conjugate base. So that's the trick. You want to form this. In the mechanism, form this right there, that intermediate. Okay? That's a lot of notes. Obviously, for the mechanism, if I'm grading this, all I'm looking at is the blue and the green. Everything else is just annotation. 5 steps. Why did I say 6 here? Oh my. 5 steps. Okay. Can you take what you see here with all its important intermediates and apply it to the same type of reaction, but now we're working with this ketone? It's not symmetrical, but you notice that the alpha carbon on the left has no alpha hydrogen, so you can't make the enolate to the left. You have to make it by removing this proton on this alpha carbon. Why don't you pause the video and draw out the full mechanism and then compare it to my answer. Okay, let's take a look at the answer. If you're concerned about timing, I was able to do that in 4 minutes and 20 seconds. So give yourself maybe 5.5 minutes. It is a bigger molecule than a typical aldol condensation. So if you could do this in 5.5 minutes, you're on solid ground. Did I do everything correct? I have 5 steps. Made the enolate, did the attack, then I protonate the alkoxide. I make the conjugate base, make the anion, and then I kick out OH minus. Ultimately, it's kicking out water. Now there is a mistake up here. If I think about what I did, there's your alpha carbon, so here's your alpha, and then attack the dot. Now the dot, I'll just use this molecule, has to the right of it CH2, CH2, CH3. Here I only have CH2, CH3. I missed the carbon. I should have that carbon right there. The phenyl group is okay. It's on the dot. Same thing here. So I think I'm good with the final product. 6, 7, 8, 9 carbons to the left. 6, 7, 8. Oh no. 6, 7, 8, 9, 10. Sorry, 10 carbons. 6, 7, 8, 9, 10. Then on the right, 6, 7, 8, 9, 10. Again, if you want to make your corrections or put a check mark if you got all of these steps correct, that is the mechanism for aldol condensation. Just on the side, if I had another, let's say, methyl group right here at the very beginning, you would realize that there would be no hydrogen here at the alpha position. You're not going to see that example many times, and I would make it very clear to my student whether I want the condensation product or you should stop at the aldol product. If this was a methyl group, to tell you the truth, and I wanted to, I asked you to do the condensation product, do a dehydration anyway, you would remove this proton, right, and make the double bond right here. Right, you remove the proton on the carbon next to the leaving group. Right, so maybe this one. Well, this one for sure. If this hydrogen was a methyl group instead. Okay. Like I said in a previous video, Knowing the aldol inside and out is going to help you with the rest of the unit, because the rest of the unit deals with aldol variations and use of the enolate.